So let's talk about the directional derivative. We know how to find the derivative with respect to x and with respect to y, so that's going to be along those vectors. But what if I want to find the derivative or the slope along a different vector or a different direction? Let me show you what I'm talking about. So let's suppose we have this graph of z equals f of xy, and I'm interested in the point of tangency right here. And I want to find the derivative in the direction of this vector instead of the x or the y vector. So I'll put a plane through that point on top of that vector. And so the angle I'm looking at, the vector I'm looking at, is the one I just drew. So that is called the directional derivative of f of x in the direction of u. Now, how do we find this? First off, some definitions. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u of the form ab. And the directional derivative is the partial derivative with respect to x times a plus the partial derivative with respect to y times b. So let's look at this. The partial derivative with respect to x times a plus the partial derivative with respect to y times b. This looks like a dot product. So I've got this vector f sub x, f sub y, dotted with ab. And ab is that unit vector we had in the first place. Let's look at an example of this. Suppose I have the function f of xy equals x cubed minus 3xy plus 4y squared, which looks like this. I'm interested in that point that I put on the graph. That's the point 1, 1, 2. And the direction I'm interested in is 3/5, 4/5. I went ahead and chose a unit vector just to make our lives a little bit easier. So let's give myself some room so we can do this. I need the partial with respect to x, and at the point 1, 1, we only need the x and y. We get a 0. Well, that's convenient, right? The partial with respect to y is negative 3x plus 8y, and at the point 1, 1, we get a 5. So now I can find the directional derivative by plugging in the numbers, and I get that the slope is 5. And if you look, you can kind of tell that it's pretty steep. It looks like it could be 5, a slope of 5. So let's try something different. I'm going to keep the function, keep the point, but this time I want to go in the direction of theta equals 5 pi over 6. The unit vector in that direction is cosine theta, sine theta. In this case, I have cosine of 5 pi over 6, sine of 5 pi over 6. Chunk it out, I get negative the square root of 3 over 2, 1/2. So let's figure out what the directional derivative with this vector is. I have all this information from the previous page. The partials will be the same, and when I plug in my point, I'll get the same values. The only difference is my unit vector. So when I do u dot my a, which is negative square root of 3 over 2, plus 5 dot 1/2, I get 5/2, which is the slope of the surface at that point in the direction of u. Well, let's look at this. It's interesting that the two partials were the same. So let's get a hold of that. Let's give that a name. We're going to call that the gradient. So this is what I want to focus in on. This is what we're going to call the gradient, which is denoted by an upside down triangle. Then it's going to be the vector of the partial with respect to x and the partial with respect to y. Or if you're a physicist, you can write it like this. So in the case of our original function, our gradient is 3x squared minus 3y, negative 3x plus 8y. Now we have another way of defining the directional derivative. The gradient dotted with the unit vector. Something that's very interesting about the gradient, which makes it worth pulling out and looking at, is the following theorem. If f is a differentiable function of 2 or 3 variables, the maximum value of the directional derivative is the magnitude of the gradient at that point. And it occurs when the unit vector has the same direction as the gradient vector. Notice I wrote x bar, not just x. That's because it represents the point in 2 space or 3 space or 4 space. That represents the vector point, not just a single x. So why is this true? Well, the directional derivative is written as the gradient of f dotted with u. So the norm, or the magnitude of that, is equal to the magnitude of the gradient times the magnitude of the unit vector times cosine theta. But u is a unit vector, so its length is just 1. So it's the magnitude of the gradient vector times cosine of theta. Now cosine of theta is between negative 1 and 1. So we want it to be 1 so that we get the maximum value. And that's going to happen when theta equals 0. And since the angle between them is 0, they must be going in the same direction. Let's look at an example. I know this formula is not going to work. If you start plugging in points, you'll go, Megan, there's no way that this is a real model for the temperature on the beach because it just doesn't make sense. Well, I fiddled with it and I played with it, and this is the best I got with, and I got tired of fiddling with it. So we're going to assume we're in an alternate reality. We're on the beach in my alternate reality. That is the temperature at the beach at the point XY. T is measured in Fahrenheit and X and Y in meters. In which direction does the temperature increase fastest at the point 1/1/2? And what is the maximum rate of increase? So you're at the point 1/1/2, and you want to figure out what it would be the worst direction to go to, where the temperature increase is the fastest. Let's go and find the gradient. The gradient of T is, again, it's a really ugly derivative, but not really, they're just numbers. Don't freak out. So the gradient is negative 5,776 times x all over 36 plus x squared plus 4y squared quantity squared times the I vector minus 23,104y over that same crap as before times the j vector. Let's get some of these numbers out of our hair. First, I can suck out 2,888 over that gross thing, and I'm left with negative 2xi minus 8yj. So at the point I'm interested in, I get this. And I also notice that 2,888 is twice of what's on the bottom. So I'm going to simplify it to 2 times negative 2i minus 4j. And this is the part I want to focus on because that tells me that the direction of greatest change is negative 2, negative 4. What is the actual magnitude? Well, the magnitude of the gradient is 2 times the magnitude of negative 2i minus 4j, but I and j are both unit vectors, so the length of that would be 2 times the square root of negative 2 squared plus negative 4 squared. Simplified, I get 4 times the square root of 5. So what have we learned? Other than Megan can't find a decent formula for the temperature of the beach at point xy, we've learned that the directional derivative of f at x in the direction of the unit vector u bar can be written as gradient of f dotted with the unit vector. I know that the gradient, if I'm in 2 space, looks something like this, the partial with respect to f and the partial with respect to y, or physicists with the I and the j. And if we're in 3 space, the gradient of f is the partial with respect to f, the partial with respect to y, the partial with respect to z, or for my physicist friends, get this. And more importantly, we have learned that the gradient gives us the direction of greatest change for the function.